Jin, then you tell me. Oh, already. Oh, you are already recording. Okay, we will start sharp. But...
So this is actually the first time I ever gave a talk on this paper.
Oh, that's
it's very strange.
I think. Yeah. Oh, good. Actually, as I said, also I was very surprised to land on your article because, as I said, I knew you because of other works, not not this one.
Right. But we all have a secret little project that we work on, right?
Yeah. Okay.
Like okay. All the number theorists are trying to prove the Riemann hypothesis.
Yeah. Okay, so let's start. Welcome everybody. So today we have great honor to have Richard Thomas talking about nodes and the Hodge conjecture. So Richard, please.
Thank you very much for the invitation. I'm going to have to put my screen down so you won't see my head, but you'll see it again later so that I can write on my screen. Okay. So I guess you probably all know the Hodge conjecture, but I state it anyway. So throughout, I'm going to have X will be a smooth projective variety over the complex numbers throughout, and I'll denote its dimension as a differential geometer would by putting a D there. So I guess that's D complex dimensions, which I guess a differential geometer might put a 2D there. Okay, and this smooth projective variety will always have a hyperplane class, so there'll be a H will be the first Chern class of the O1 line bundle. So I'm assuming it's projective, so I can pick an ample line bundle. And throughout, I will use the notation HPPXQ for what are called the Hodge cohomology classes. So this is the rational cohomology in degree 2p intersected with the pp part of the complex cohomology. So this is an intersection inside H2p x with complex coefficients. Okay, and then the Hodge conjecture states that given any class in this HPP with rational coefficients, there should be some rational linear combination of codimension-p subvarieties such that A is that rational linear combination of their Poincare jewels or their fundamental classes. Okay, so maybe I'll just remind you this is essentially the Poincare jewel of the fundamental class. Of the Zi. So what you do is, I mean, Zi might be singular, but so it's important to use homology. So I would take H2D minus 2p. So that's the top dimensional homology of Zi. That's where its fundamental class would lie. And then I push it forward to the homology of X. And then I use Poincare duality. This is push forward, this is Poincare duality, and this is H2p of X. Okay. So all these Hodge cycles can be represented are algebraic. So Hodge classes, that's the A, are algebraic. That's the Zs. So they're a linear combination of Zs, of subvarieties. Okay. And there are a bunch of points to note. So the converse is kind of trivial. So if you have these an algebraic class, this sum of Zi's here, some combination of Zi's, then it's immediately Hodge, because so any subvariety, its fundamental class, sort of an easy exercise to show it actually lies in these Hodge classes. Okay, and the easiest way of saying that is to use the pairing on cohomology. By integrating Z against 2n minus 2p cohomology classes, you see that the only ones which give something non-zero in the Hodge decomposition are the ones of the form n minus p comma n minus p. Only any other cohomology class of other Hodge types integrates to 0 on the Zi. So under duality, that's this statement here. Okay. What else do we know? It's true in codimension 1. In fact, over the integers, you don't need to use the rationals in codimension 1. So this is the Lefschetz 1-1 theorem. And it's therefore true by hard Lefschetz. And this Lefschetz 1-1 theorem implies it's also true in the complementary dimension, so p equals d minus 1. So in the first case, for p equals 1, you're producing divisors. And we know that this 1-1 condition means that A defines a holomorphic line bundle, at least over the integers. And then using the ample line bundle, we can always produce sort of meromorphic sections of that line bundle. And so we can produce divisors representing A. Then when P is D minus 1, that's curves. We're trying to produce curves. And the way we do that is very easy. Associated to a curve class, so an H2D minus 2 class, you write it as an intersection of hyperplanes times by a divisor, and then you produce the divisor by the Lefschetz 1-1 theorem. Okay, so hard Lefschetz tells you that when P is D minus 1, all these classes A can be written as an intersection of H classes, hyperplane classes, times by a divisor class, which we've already handled by Lefschetz 1-1. Okay, and it's not true over Z in general. So you have to use Q. And any questions about this? Is everyone happy with the Hodge conjecture, or should I spend more time on it?
Yeah, I think that's okay.
Yeah. So I kind of half expecting someone to ask if I believe it. I have absolutely no idea. There's almost no evidence for it, except that there's this sort of body of beautiful theory developed by Grothendieck and others, which makes it fit into a coherent form, a coherent set of other conjectures, many of them arithmetic, and they all fit together so beautifully without any apparent contradiction that the assumption is they must be true. However, there's very, very little evidence for them. Okay, so the theorem I'm going to talk about today is the following. So I'm not going to talk about the Hodge conjecture for one variety. I want to talk about the Hodge conjecture for all varieties all at once. You'll see why, because I'm going to do an induction on dimension. So in order to understand the Hodge conjecture for one variety, I need to use the Hodge conjecture for various other varieties, like its hyperplane sections, bigger varieties of which it is a hyperplane, things like that. Okay, so the theorem is that the Hodge conjecture for all varieties X and for all classes A is equivalent to the following statement. So for all varieties X, but of even dimension. So I'm only going to consider the Hodge conjecture in even dimensions. And I'm only going to consider Hodge classes in the middle dimension. So that's the first thing. I don't need to understand the Hodge conjecture for general X. In order to understand the Hodge conjecture for general X and general Hodge classes, it's enough to understand it for even dimensional X and middle dimensional Hodge classes. And then for those, what I need to prove. Sorry, did someone ask a question? No, someone's got their microphone on. Okay. And so and then for these middle dimensional classes, I don't need to prove the Hodge conjecture for those either. So I don't need to find a subvariety which represents them. All I need to do is find a single hypersurface which contains them. So there exists, I'm going to leave a gap, but it's true without the gap. So there exists a hypersurface D okay, there exists a hypersurface such that A is in the image. I'll explain this in a minute. Okay, so that's the theorem I'm going to prove today. So just a few points to explain what the theorem says. Firstly, D will be typically singular. So it's important to use homology. You don't have Poincare duality for D, so I'm not going to use the cohomology of D. I use the homology. Okay. Another thing is it's important, as I mentioned, to do for all X at once. Theorem is not true if all X is replaced by 1X. Okay. So if I want to prove the Hodge conjecture for 1X, is not enough to prove this hypersurface statement for that X, or in fact for some other X. You've really got to do all at once. So maybe okay, so the Hodge conjecture for all varieties X and all Hodge classes A is equivalent to this statement in the brackets here. Okay. And then I'm going to write here nodal, because that's what I'll prove today. But the theorem's true with or without nodal. In general, D will be singular. You can, if you wish, constrain the singularities of D, or you don't have to. If you prove it for crazy arbitrary singular D, that's absolutely fine as well. But it just turns out that you can make D nodal. That's the best you can do. You won't be able to make D smooth, but you can make it nodal, so you may as well, because then it's easier to understand. Okay, so I'll remind you what nodal means later. So a hypersurface with the simplest possible singularities, just quadratic singularities at one point, at some point, some isolated points. Okay, and then the other point I should make about this is that the moral way you should think about this is that one, we restrict. It's enough to restrict attention to even dimensional varieties and half dimension classes. That's the first thing. And then the second thing, so that's kind of standard by certain Lefschetz theorems, as I'll explain in a minute. But the second thing, which is more striking, is that instead of trying to find a whole bunch of algebraic equations cutting out a representative of A, so if A is codimension n, then usually you'd require more than n. It won't be a global complete intersection, so you'd need more than n equations. So instead of trying to find, at least n holomorphic or algebraic equations cutting out a subvariety that the class A, or its Poincaré dual, maybe I'll use its Poincaré dual. Let me think of it as a homology class, can be sort of squeezed into. So instead of trying to cut out a subvariety and then finding that A is in the homology of that subvariety, it's carried by that subvariety. Okay, we need only to find one equation such that the Poincaré dual of A can be squeezed or found in, squeezed into its zero locus. Okay, so we only have to find a hyperplane. We've only got to find one equation, and that will then be global. Hypersurfaces are cut out by one global equation, by a section of a line bundle. They really are global complete intersections. And but we have to find it carefully. We're going to have to choose it to be singular, unfortunately. Otherwise, it won't carry A. So singular hypersurfaces contain more middle dimensional homology, or more, two-end dimensional homology than smooth ones. Okay, so that's the moral. And then I just, before I sort of check if there's any confusion about this, I'm just going to give a key example where this theorem is really clear and obvious. Okay, so the key example is the case we already know, essentially Lefschetz 1,1. So we take n equals 1. Okay. So we're taking a surface. So x2n is a surface, and we're looking for curves. So divisors or hypersurfaces are then curves. So D will be a curve. And we're trying to find a curve containing our two-dimensional homology class. So in this case, im of h2d goes to h2x, where this is a surface. So it's even dimensional, complex surface. Okay, this is all automatically entirely algebraic already. So I'll draw a picture. So here's my surface X, and here's my D. Maybe it'll have irreducible components. I've drawn two in this case. So D here is I've got a D is union of D1 and D2. Okay, so in this case, basically what happens is, if D was smooth, or in fact even irreducible, then the image of H2 of D in H2 of X would just be the fundamental class of D and its multiples. So you have to take D to be reducible, and in particular singular, and then suddenly the image becomes the fundamental classes of the components, the irreducible components. So this is the span of the DIs. Oops. Over Q, where D is the union of DIs, or its irreducible components. Okay, And so here it's kind of obvious. The theorem's kind of obvious. On the one hand, if this statement in the theorem at the bottom, the statement in brackets here, is true, that means my class A is in the image of H2 of D, well, then it must be in the span of these irreducible components DI, and therefore it's algebraic. Therefore, it's a linear combination of algebraic varieties. Conversely, any smooth, oh no, you don't even need smooth. Okay, any curve, the Hodge conjecture in this dimension is only concerned with curves in my surface, or linear combinations of curves. So any algebraic curve in X is contained in a hypersurface. Okay, so it's curve C in X is contained in a hypersurface. Okay, so I can always take a very, very ample hypersurface to contain the curve, and then it will split into that curve plus some other algebraic pieces. Okay, so that means that my curve is indeed in the image of the second homology of the divisor, because the fundamental class of the curve there is an element of H2 of D, which then pushes forward to the curve class in X. Okay, so the point is, as you can see in this low dimension, these singular divisors, in this case reducible, contain more of the relevant homology, the middle dimensional homology of X, than smooth divisors do. And so that's how the theorem works. In higher dimensions, these divisors D will not be reducible. They will have more elaborate, the way the homology is contained in them will be more elaborate. We'll see that later. We'll see why these nodal and singular divisors contain more homology. But the statement is that you can always force them to contain any algebraic or Hodge class. If the Hodge, these divisors contain any algebraic or middle dimensional algebraic homology, and the Hodge conjecture is that they contain, that is equivalent to them containing any Hodge cycle. So maybe I'll just go up here to the statement of the theorem. Does everyone understand the statement of the theorem? Are there any questions about it?
So in the case of surfaces, if even the D is irreducible, it will give a trivial Hodge cycle. So, but in the higher dimension, I can, even if D is irreducible, it might encode the many non-trivial Hodge cycles, I think.
That's right. Yeah. In higher dimensions, you should think of D as being irreducible, but nonetheless containing more of the middle dimensional homology of X. So the moment it's nodal, in surfaces, it's reducible as the key issue. In higher dimensions, it's nodal that's the key issue. That's what forces it to contain more homology.
Okay, thanks.
Yeah, that's great. Okay, so this is the theorem I'm going to prove. So to start with, I'm just going to do some standard reductions. These aren't very interesting. So you could go and make a cup of tea for 5 minutes while I do these standard reductions. I'm not sure whether to include them or not, but anyway, I just show you some standard things to kind of simplify the statement of the Hodge conjecture. So firstly, any algebraic cycle, let's suppose, you know, over the rational numbers, so rational linear combination of fundamental classes of codimension-p subvarieties can be written. You can make it effective, more or less. So instead of having lots of pluses and minuses, it can be written as just in the following way. So you could take some, after you pass to a large multiple, firstly to clear all denominators. So you don't have rational combinations, you have integer combinations. And then you go again, you pass to an even higher multiple. Then you can arrange that it's the fundamental class of an actual subvariety, so that's effective, up to some multiple of h to the p. So h, remember, was the standard hyperplane, and you intersect that p times. Okay, and here n1 and n2 now are really positive integers. Okay, and z is really a codimension-p subvariety. Okay, so we don't have to take all these crazy rational combinations up to multiplying by a big integer. We can just say, once you add enough copies of the appropriate power of the hyperplane class, then you can assume you've really got an effective algebraic cycle. Another reduction is that you can choose this z to be smooth when it's less than half dimensional. No, when it's less or equal to, when its dimension is less or equal half the dimension of x. But I come back to that in a minute. Okay, and then maybe I'll just say something about this. So the key point to prove this is that the ideal sheaf of the union of all these zi's, let's take some high power of it, some power of it, so I can get in all these multiples of the zi's. Once I twist it up by some huge n, this has lots of sections. Once n is large enough. Okay. So what do those sections cut out? So we get hypersurfaces containing the zi's, or in fact multiples of the zi's. And we intersecting p of them gives a relation like n. So I take my divisor class, my hypersurface class, n times h, intersect it p times, and this is some positive combination of the zi's plus some effective thing, which will eventually become my z in this statement up here. Okay, so that gives you what you want. Okay, so that's the first thing. Up to adding multiples of the hyperplane class, we're not looking for arbitrary cycles. We're really looking for effective cycles. Okay, with integer coefficients. So that's one simplification. Another is that the Hodge conjecture for all varieties x in low codimension, so that's where this p in the HPP is less than dimension over 2. This implies the Hodge conjecture for all x in high codimension, p bigger than d over 2. All right. So to prove the Hodge conjecture, you only need to prove it for low codimension classes. So for you only have to produce algebraic varieties of bigger than half the dimension and above. So big subvarieties of small codimension. Okay, and this is also very easy to prove. This was how we proved earlier that the Lefschetz 1-1 theorem gives you the Hodge conjecture in 2 degrees, not just for divisors, but also for curves. It's the same proof, so I'll just give it now. So you take your A in HPP XQ, where P is bigger than D over 2. So we start with our high codimension class, and we're going to try and prove it from a low codimension class. So this A equals A primed dotted with some powers of the hyperplane class by the hard Lefschetz theorem. Where A primed is in H, let me see my notes, D minus P. Did I get the numbers right? Okay, exercise, check I got all the numbers right. Okay, so the Hodge conjecture for A primed, in other words, A primed is in low codimension. Sorry, was there a question? No. So the Hodge conjecture for A primed, which is the Hodge conjecture in low codimension, gives it for A. So, you know, I apply the Hodge conjecture for A primed, I produce some algebraic cycle representing A primed. Now I just intersect it. I just intersect the algebraic version, the algebraic subvariety produced for A primed. I intersect it with 2p minus d copies of H, or 2p minus d hyperplanes, hypersurfaces. Okay, so that's easy. Was there a question? I'm not sure.
No, I think that's okay. Nobody.
We're okay. Okay, and then the final reduction, which is a bit more tricky, is going the other way. So if I now only need to prove the Hodge conjecture for these big subvarieties. I only need to produce these big subvarieties. Now what I'm going to do is show that actually I only need to do it for the middle dimensional ones. So what we have now is that the Hodge conjecture for all varieties X in dimension D minus 1 in low codimension, because I only now care about low codimension, because that implies high codimension. This implies the Hodge conjecture for X of 1 dimension up in low codimension. Okay. So to prove the Hodge conjecture for XD, I can actually deduce it from the Hodge conjecture in 1 less dimension, from a smaller variety. Okay, by passing to hypersurfaces. So let me show you that. So how does the proof go? We just pick a Lefschetz pencil. Okay, so we pick a pencil of hyperplanes. We blow up in the base locus. So hyperplanes HT, we blow up in the base locus. And we end up with a pencil, we end up with a vibration over P1. Okay, and the blowing up does almost nothing to the column. We understand how that changes the cohomology. It really doesn't affect much. Okay. And now what we're going to do is assume the Hodge conjecture for the fibers of this Lefschetz pencil, for the XTs. Okay. So if the Hodge conjecture is true for the fibers XT, well, let me do it for the smooth fibers. That's enough, because I only want the Hodge conjecture for smooth varieties. So if it's true for lower dimensional, the D minus 1 dimensional guys, then I'm going to prove it's true for X. Okay, so the Hodge conjecture is true for that. Then what I find is, then you know there's some N1 depending on T times A plus some N2. So the usual thing, I have to multiply up by some big integer. I have to add on a bunch of copies of intersections of hyperplanes. Then this guy, restricted to XT, is now, by the Hodge conjecture, algebraic. It is the fundamental class of a subvariety in XT. Okay? But now, now I've got to let t vary and stitch these zt's together. How am I going to do that? Well, the first thing, I've got this worry that this n1t keeps changing with t. Okay, but that's easily fixed. These n1t and n2t's are countable, whereas the t, which lies in P1 minus the discriminant locus, is uncountable. So then it's obvious that there exists some n1 and n2 which work for infinitely many t's. Is effective algebraic for infinitely many t in P1. Okay, and that's enough now, because everything's algebraic here, to say that if I form, if I form the relative Hilbert scheme, so the Hilbert scheme of the fibers of x hat over P1 in the class, n1a plus n2 h to the p, if I form that Hilbert scheme, which is proper over P1, it's onto infinitely many points in P1, therefore it's onto P1. So it implies that this is actually surjective. You can't be onto infinitely many points without being onto the whole thing in algebraic geometry. Okay, so it's surjective. Furthermore, it's also projective by Grothendieck. So there exists a multisection. Okay, so I can't pick a section necessarily to stitch together. A section would be a ZT in each fiber, and then I would sort of glue them all together. I can't necessarily get that, but I can certainly get an R section by because it's projective, it has a hyperplane. I just keep intersecting hyperplanes until I get down to something which is a curve. Okay, so I end up with an R section. Okay, and so now using that R section, pulling back the universal subvariety parameterized by the Hilbert scheme, using the fact that the Hilbert scheme is a fine moduli space. Okay, what this means is, by the universal property, there exists a Z in X hat, some subvariety, okay, such that whose restriction to every fiber, or at least for infinitely many fibers, the generic fiber, let's say, is R lots of my class, which is good enough. Okay, because by Lefschetz, there's always Lefschetz in this subject. This sequence of maps here, pulling back to H2P of X hat, and then restricting to a fiber, this is an isomorphism. So what we actually find is, what that tells us is that pushdown of this class Z is actually, it's not just our class R times N1A plus N2 H to the P on the fibers XT. It's not just true on the fibers, it's actually true on the whole of X. Okay. So that was my S side. That was this proof that actually the Hodge conjecture, now we're only working in low codimensions, so less than half those, where the codimension is less than half the dimension. Okay, so we're only finding these big subvarieties. And what this proves is, if you can find them on hyperplanes, if you can find them on one lower dimensional varieties, then you can find them on your X. Okay, so by Lefschetz penciling X, if you can prove a class is algebraic on every member of the pencil, then you can stitch them together and prove it's algebraic on the whole of X. Okay, so now by an induction on dimension, I can keep going to lower and lower dimensional X until this codimension is precisely half the dimension. Okay, so by induction, we get to half the dimension. We get to the following proposition: the Hodge conjecture for all x, d, and a. This is essentially the first statement in my big theorem at the start, the main theorem at the start, is that proving the Hodge conjecture for any dimension, any class, is true for proving it for all even dimensional varieties and all half-dimensional Hodge classes. And what do we have to prove for those? We have to prove there's an N1 and N2 and a subvariety such that our class is that subvariety up to adding appropriate powers of the hyperplane class. All right, so that's effectively what we've sketch proved there. So we've sort of proved half the theorem. We've got down to these middle dimensional classes in even dimensional varieties. So any questions about that? That was the reduction to this even dimensional and middle dimensional subvariety case. Okay, so now we're ready to sort of go to the proof of the main theorem. So firstly, I'll do this direction. Okay, so what do I have to do? I have to suppose this Hodge class in the middle dimension of some even dimensional variety. I'm supposed to suppose it lies in the image of the homology of some divisor. Okay, and for now, as I said, I could take this divisor to have any singularities I like, but today what I'll do is I'll prove the special case where D is nodal. Some nodal D, nodal hypersurface. So just an aside, nodal means smooth except at isolated points. It looks analytically, locally analytically, like sum zi squared equals 0. In what are we in? I'm in dimension 2n, so I'm going to go for x to the 2n, and I'm going to take a non-degenerate quadratic form. So I'm going to go from I equals 1 to 2n. So the hypersurface has this quadratic singularity at finitely many isolated points and nothing else, otherwise it's smooth. Okay, so I'm supposed to assume that I've managed to find this hypersurface which contains A as a homology class. So I haven't managed to contain it as an algebraic variety yet, but that's fine. I can now continue with my Lefschetz induction on working on D. So I resolve D. That doesn't change its form.
Just a question. Can you insert in your theorem the maximum amount of these nodes which might appear? I mean, it must be at most 10 or something depending on it.
No. No, essentially because I can't control these N1s and N2s that I keep writing down.
Okay.
Yeah, you'll see the number of nodes in a minute. In about 5 minutes, I'll show you what the number of nodes is, but there'll be one of these big N's in there. I'll have twisted something up, and that's what I can't control. But you'll see in a minute. Okay. So firstly, I resolve D. And then the reason I took this nodal guy is because then by explicit analysis, we know how to resolve nodes. So we know what the resolution looks like. Shows that there exists a lift A hat in H N N D hat. Actually, I'm not sure I mean N. I don't mean NN, do I? That's incorrect. That's incorrect. It should be. That should be N minus 1, N minus 1. Okay, such that pi star A hat equals A. So I can lift it to some, because it's a Hodge class. On X is and it lies on D, I can show it lifts to a Hodge class on D hat. And this is where nodal is useful, but as an aside, if you're interested in allowing Ds with worse singularities, so if D has worse singularities and nodes, then you can prove the same theorem, but you have to use, the power of Deligne's mixed Hodge structures. So the fact that this pi star map here on mixed Hodge structures is strict. A strict morphism of mixed Hodge structures means you can do this, but that's sort of beyond the. That's technically much more complicated than I need for today. So I'm just going to talk about Ds with ordinary double points with nodes. Okay, so we have this Hodge class on now a new smooth variety D hat. Now that's fine. Now we can just continue with induction. So, but D hat. So the dimension of D hat is 1 less, of course. It's 2n minus 1 now. So by induction, so I've managed to get now down to a Hodge class of lower codimension, higher dimension on a variety of lower dimension. And so now I just carry on with my induction again. So my induction on dim X, I can just carry on. Can assume the Hodge conjecture is true for D hat and A hat. So we just carry on with our standard Lefschetz hyperplane induction. Okay. So we get an algebraic cycle Z on D hat, and we push it forward first to D and then to X. So pushing forward to X gives, our class A. Well, really it'd probably be some N1A plus N2H to the N. All right. So all this hyperplane is about, in the theorem, is about allowing you to continue the induction. If you can find your homology class in the hyperplane, then you've managed to cut down 1 less dimension, and you just go again. You carry on doing your induction, your Lefschetz, either cutting things down by hyperplanes or fibering them by Lefschetz pencils, and you just go again. So you just do an induction on dimension. And eventually you get down to, finding curves in surfaces and Lefschetz 1-1 theorem. Okay, so this hyperplane allows you to continue the induction, which you thought got stuck at the middle dimension. So all these Lefschetz tricks and hyperplane tricks allowed you to get from either low or high dimension to the middle dimension, and then you think you're stuck. But if you've got this hyperplane, this singular hyperplane, then up to resolving it, you can go again. You're not stuck. You've now got a new cycle that you can apply the induction to again. Okay, so that's one direction. And that's in some sense the hard direction. But the so-called easy direction is in some sense more interesting, and it shows you where nodes come from. Okay, so in the easy direction, we're supposed to assume the Hodge conjecture. So we've assumed that by the Hodge conjecture, we have our subvariety Z in X, such that Z is A, up to the usual, multiplication by n, adding copies of h to the n. Okay, so we have our Z. And now I'm going to try and show that there's a nice hypersurface or nodal hypersurface containing this Z. Well, the first thing to do is to smooth Z. So Kleeman shows that you can smooth, you can assume that Z is smooth. If its dimension, well, if p is bigger than n-1. In particular, in the half-dimensional case that I'm interested in, you can assume that p is smooth. So that's an argument due to Kleeman. So let me just sketch it. What you do is you say, well, this z could be horrific, but we can try and resolve it by nicer things. So what we do is we resolve OZ by copies of, in the sense of a homological algebra, by copies of sort of O minus K sheaves. Okay, so, the usual way, you just say O of Z is a quotient of O of X. And now I've got to resolve the kernel of that map. So I've got I of Z. So how do I resolve that? I twist it up, I take sections, and then I evaluate those sections. Okay. And that map, for K large enough, that will map onto the ideal sheaf of Z. And now I do the same. Now I look at this map, I look at its kernel, I twist it up by some huge K, I take sections, and I evaluate those sections. And so I keep resolving, I just go on and on. Okay. Until the kernel, so once I've gone sort of n times or 2n times or something by the syzygy theorem, until the kernel is locally free. Okay. Okay, so eventually I'm going to get a nice vector bundle. So I started with this structure sheaf, this horrible thing, this structure sheaf of some singular subvariety. Eventually I get a vector bundle. And then I'm going to twist up. So the key point about that is that the pth Chern class of this vector bundle, even if I twist it by some large power of the ample line bundle, is because what I've got this resolution, right, with a k at the end. So I end up with 0k dot dot dot. And all the other terms are just vector spaces tensored with things like O minus k. So they're all producing just powers of the hyperplane when I take Chern classes. So the only things which don't do that are k and O of z, all right, in this resolution. So what I find is that the pth Chern class of k is up to constants just z, up to multiplication by numbers and adding powers of the hyperplane. Okay, so now I end up with this pth Chern class of it. I can replace z by this pth Chern class of this nice vector bundle, and then once n is sufficiently large, k of n has lots of sections. And so you can pretend these sections, once n is huge, you can pretend these sections are generic. You can almost pretend, you can do transversality results, okay? And it has so many sections that Kleeman shows that generic choice of this many sections have degeneracy locus. So that's where they become linearly dependent. So generically, they're linearly independent. And you look at the locus where they become linearly dependent, where the minors of the matrix vanish. So they have degeneracy locus, which is a smooth representative of this Chern class. So long as P is bigger than n minus 1. Okay. So if you don't like that argument, you can ignore it. It's just saying you can choose everything generic so that Z is smooth. You may as well assume Z is smooth. And then the very last thing is I'm going to show why this means that you can contain Z in a nodal hypersurface. Okay. So now can as usual, I'm reusing this large N. It can always get bigger. Okay, so why is that? Why can we squeeze it in? It's essentially because of the following. So what am I interested in? I'm interested in sections of O of N, so that's hypersurfaces, which vanish on Z. So they contain, the hypersurface contains Z. So I'm interested in this vector space, and I'm interested in its restriction to Z, which is what? That's just sections of IZN divided by IZ times by IZN. That's IZ squared, which is sections of the normal bundle to Z dual twisted by N. Okay, and so I'm interested in this, and I'm interested in taking sections here, and what do they map to here? They map to the derivative of the section restricted to Z. Okay, so remember, if the section vanishes along Z, then its derivative is firstly well defined. You don't need a connection on this bundle, this line bundle O of N, because you're working at the zero section. So the connection's always everything's independent of connection. So the derivative makes sense along the zeros of S, okay, which contains Z. So along Z, the derivative of S makes sense as if S was just a function. And then the derivative of S vanishes in the tangent directions to Z, because S vanishes along Z. So actually it descends to, it doesn't just take values in the cotangent bundle of X restricted to Z, it takes values in the conormal bundle to Z, because it vanishes on the tangent bundle to Z. Okay, so this is the map which takes S to DS. And the point about this map is it's onto for large N, such that it's onto as soon as H1 of IZ squared twisted by N is 0, which you can arrange by taking N very large by whatever Sayre's theorem B or A or something. Okay, so what you find from this is just the last sentence effectively. So what this shows you is that the generic section on the left-hand side, by studying the right-hand side, which is for large N is generated by sections, the generic section has 0 locus. Yeah, so I don't mean implies that. So on the right, let me start again. On the right-hand side, look at the sections on the right-hand side. the right-hand side, there's sections of this rank. This is a rank P bundle on Z, where Z has dimension D minus P. Okay, and it's a very positive bundle. By twisting up by n very large. Okay, so what that means is the generic section of this thing on the right hand side has 0 locus of dimension D minus 2p on Z, which means it has no zeros if p is bigger than d over 2. So when your codimension is large and your variety Z is very small, then it has no zeros and it has isolated reduced single point zeros in the half-dimensional case that I'm interested in. Okay, and so now by Bettini, the generic S, remember this map from S to DS was onto, so if I lift one, the generic lift as D is smooth everywhere. Because the base locus, you see, of these sections, which vanish on Z, these sections in the left-hand side, the base locus is just Z. So Bettini tells you the only place you get singularities in the generic element is along Z. And then I've analyzed them along Z to see when you have zeros. If you have no zeros of the derivative, then by the Jacobian criterion, you're smooth along Z. So Bettini gives you smoothness away from Z, and then the Jacobian criterion gives you smoothness on Z. Okay, whereas in this case, Bettini theorem tells you you're smooth away from Z, and on Z, when you get these reduced isolated zeros of the derivative, that means you have these quadratic singularities and nothing else. So you get nodes on Z. And to answer Hussein's question, the number of nodes is the number of zeros of this DS restricted to Z. So it's the top Chern class. I'll write it down. So the number of nodes in the half-dimensional case is the top Chern class, so that's Cn of this normal bundle to Z in X dual twisted by big N. And we can't control that because I don't know how big I have to take big N. Okay. So the upshot is, this is the end of the proof, because what I've done is I've shown that if the Hodge conjecture is true, then I get this algebraic cycle Z, and then I can always squeeze it into a hyperplane, and I can choose my hyperplane. But after smoothing Z, I can choose my hyperplane to have nodes and nothing else, no worse singularities. So I'm done. Okay, I'll stop there.
Okay, thank you, Richard. Any question? So we have a question session in the recorded and unrecorded one.
Sorry, my computer died for a second. Did you lose me?
No, you are still there.
Right.
Okay, Jean, can you stop recording? Maybe let's just discuss in the non.
Okay.